All right. So for math this week, there's only one thing that's really due. The second thing I would like you to complete as well, though, is that mental health and wellness break assignment. The only other thing that's due will be a lesson two quadratics assignment there. And that is the quadratics quiz. And I will try to get your other stuff marked ASAP here. It might be marked Wednesday, Thursday, Friday. I'm not sure. And then I'll also release kind of our schedule that we're heading into for this next week. I'm imagining that we'll meet up tomorrow, and then that will probably be it for the meetings for this week. I want to go over number three here, lesson three, and then we will get we'll do the quiz this week, probably the assignment or the exam next week, and then we'll keep progressing through math here. So, just a refresher of what we learned. We learned about this particular equation here: y is equal to a bracket x minus p squared plus q. And we said that that was vertex form. We said that p and q represented the x value of the vertex, and q represented the y value of the vertex. And the one confusing thing that we said was interesting about this formula was this negative sign. That negative sign there, if P is positive, so if the vertex is in the top half of the graph, it's a positive value, then it will show as x minus P bracket squared. If it is a negative x value, then it'll be x plus P. So that was the one confusing part of what we talked about last time. So with looking at these notes here, what we are asked to do first here is we're asked to use a table of values to graph the following functions. And the reason that we're going to do that is we want to look at the shape of the parabola. So previously we spent a lot of time focusing on P and Q. Today we want to focus on A. So table of values for both of these that we want to make, we have our y values and our x values. And then over here, we'll do the exact same thing, y values and x values. Okay, and so what we want to check is we want to see at each y value or at each corresponding x value, what will y be? So at x is equal to 0, y will also be 0. So we know that we can plot that point here. If x is 1, 2 times 1 squared is 2, and that's it. If x is 2, 2 times 2 squared would be 4, so 2 times 4 is 8, so our y value would be 8. Next point, let's say we try 3. 3 squared, and then 2 times 9 then would be 18. So we have that list of points there. And so what we can start doing is, again, notice I've only plugged in the right side of this. I've only plugged in numbers going this way on the x-axis. There's a reason for that. The axis of symmetry lies along the vertex. And because we don't have actually any p value or q value in this case, we know that the vertex of this particular graph, the vertex will be equal to 0, 0. And looking at this exact equation as well, we also know that the vertex of this graph will be equal to 0, 0. We don't have any x minus p. We don't have anything other than an a value and an x squared. We don't have any p and q to graph. So I knew that the vertex would be 0, 0. I graphed or calculated a table of values for points only going this way along the x-axis. So we can plug in those points. We have 2, 1. So when x is 1, y is 2. When x is 2, y is 8. And when x is 3, y is 18. And so I can do the same thing on the other side. -3, 18, 2, and 8, 1, and 2. And so what we end up getting here is when we have the equation of y is equal to 2x squared, we get a really, really skinny and tall graph. And part of the reason is that as x is increasing, because x is squared here, it has an exponential increase that's impacting the y value. So it's not like it's going up 1 for 1. Every time x goes up 1, y is going up quite a bit. It went up by 2, it went up by 6, it went up by 10, and that would continue on forever and ever. The points would get further and further vertical as the x values increased. So that's when we have a value above 1x squared. Now we're going to look at when we have a value below 1x squared. So again, if x was 0, y would also have to be 0. If x was 1, well, then 1 squared is 1. So we would get a value here of 1 and a y value of 0.5. 5. If x was 2, 2 squared gives us 4. Half of 4 is 2. If x squared was 3, 3 squared is 9. Half of 3 is 4.5. And so what we end up getting here is we get a graph that looks like this. It starts at 0, 0. At 1, y is 0.5. At 2, y is 2. At 3, y is 4.5. I guess let's do one more point here. So 4. 4 squared is 16. Half of that is 8. So at 4, we would have the point 8 here. I can do the same thing on the negative side. Negative 4, 8. 3 and 4.5. 2 and 2. Negative 1. And oops, let's do that point a bit more accurate. 0.5. And so what we end up getting here is we get a graph that looks quite a bit wider than what we previously saw. Kind of what I want you to focus on here is if you look at the vertexes of both of these graphs, so if you look at this vertex here and this vertex, they have very, very different shapes. The y is equal to 2x squared one is very narrow. The y is equal to 1/2 x squared is very, very wide. And if I were to pull up Desmos, we could see that that pattern would continue. So if I have 2x squared, that's what that looks like. That's what the graph of 2x squared looks like. And if I do 1/2 x squared, the graph is slightly wider. And it's easier to tell that if we're zoomed in right here. So that's the graph of half x squared. Here's the graph of 2x squared. So again, just the width of the graph, that's the main thing that's changing. And that is all being impacted by the variable a. So that's all changing the shape of our graph. The a value can be multiplied by the brackets x minus p squared to determine the shape of the graph. Basically, what we want to see is if we have a graph or if we have an a value equal to 1, that's a normal width. Normal width. If a is greater than 1, that's a skinny graph. And if a is less than 1, that would be a really wide graph. So that's just comparatively what you can see. The other thing that we need to consider when we're looking at a is a positive a value or a negative a value. If a is in fact positive, that will open up the graph up. If a is negative, that will open up the graph down. So that's previously what we had talked about and what we had seen earlier last week. But the reason that you want to multiply a by these brackets is, well, what happens if all of a sudden in our brackets we have negative x plus p squared? I can't arbitrarily tell whether this a value, this ax squared, will be either positive or negative. Ideally, we want the form of our graph to be y is equal to ax squared and then a bunch of stuff after that. It doesn't really matter what follows, but we want to be able to see this a value for what it truly is. Basically, we want to unmask the a value and find out the real identity of Spider-Man. So what we're going to do for these couple of graphs here is we are going to fill in the information about the quadratic, and we are going to sketch each of the graphs. So looking at this first, f of x is equal to negative 3 x minus 1 squared plus 10. Right away, I can already tell that this a value is negative here, and we're going to be multiplying it by a positive x. And so as such, I know that if it's a negative a value, this graph will be opening down. This parabola will open down. I also, just looking at this, can see the vertex. Again, remember that if this is minus 1, that serves as a positive 1 value for our vertex. And then we have a positive 10 in terms of our vertex where it sits on the y-axis. In terms of finding x and y intercepts, we could solve for that, or we could graph it and figure out where this graph is going to be, that sort of thing. Y-intercept, same thing. We could set x equal to 0, which we will do, and then we'll solve for. Axis of symmetry, we said that we can always solve for that one. That one's always x is equal to whatever the vertex is. So in this case, x is equal to a positive 1. Domain, we can always solve for that. It's always XER. So if I was graphing this particular one, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 1 over. My vertex is going to be right about there, is where I'm guessing the vertex will be. So looking at this, I also know that this is going to be opening down. So I know that I will have one y-intercept and two x-intercepts. The goal would be to find out what both of those are. So to do it, we are going to plug that exact equation into Desmos. And so the equation that we were working with was -3 bracket x minus 1 bracket squared plus 10. And you could see that our vertex here falls at the point 1 comma 10. Our y-intercept is 0 comma 7. Our y-intercept is 0 comma 7. We said that there was one of those. We have two x-intercepts that we're dealing with here. One of the x-intercepts is 0, negative 0.826 and 0. So negative 0.826 comma 0. And the other value that we found was 2.826 and 0. 2.826 comma 0. Like such. Okay, and then in terms of the range, we know that the range will be YER. And the other feature of this graph is that Y will be less than 10. Less than or equal to 10. Because we know that the parabola is shifting down like such. The other thing, because we're focusing on A, that we want to notice is that this parabola, when we look at this vertex, is quite skinny. If I were to remove that -3, we can see how much that widens up and how much that narrows up when we change the value of A. So when my value of A is 3, it's quite skinny. When it's wider than that and it's just -1, then it's quite a bit wider graph. So that's kind of the focus of what I wanted us to see there. Let me take a screenshot of this particular graph and insert that for you. There. Where did I end up here? Make this quite a bit smaller. And we'll put it right there. Awesome. So there you can see the actual graph, what it actually looks like on the side. So that's our first little example there. On your quiz, you'll notice that there's 3 examples that say, is this a parabola, or circle which one is the parabola. Again, when we're looking at parabolas, we want them to have the qualifications of extending forever. So if there is an answer that looks like this and it stops here, that's probably not a parabola. Parabolas would typically extend forever. So what that means is that there's probably something called a vertical asymptote, or there's some sort of limitation that would prevent it from exceeding over this point of 6. So again, you want your parabolas to extend forever, and you want them to have either the smiley upwards or the downward smiley face. So what we want to do is we want to be able to write the equations of these parabolas. And so this is where it gets a little bit more tricky. But the first step that I would do when I'm looking at these problems is I know that I can write them in vertex form. I would want to look at wherever these vertex points are and start solving those. So I know that my format of these will all be y is equal to a times x minus p squared plus q. I know that for each one of these graphs, I need that formula. For each one of these graphs, I need that formula. And so what we're going to try to do then is we can plug in the values of P and Q because we know what those are. And then we could try to solve for A. So what we're going to do is we're actually going to steal a point. We're going to steal this point right here. And we're going to try to solve for A to figure out what it is. Because arbitrarily looking at this graph, it's very difficult to say, I know exactly what the slope of this graph is. I know exactly what it is. I can solve it right now and there. So again, we're going to take this and we're going to plug in our blue point. Our blue point had a y value of 1. We don't know what A is yet. Our x value of that point was 2. And then in terms of solving for our vertex, the x value was 0 squared. And the q value of our vertex was -1. So solving this, we have 1 is equal to a times 2 squared minus 1. I would add 1 to both sides to get the a times 2 squared by itself. We'd end up with 2 is equal to 4a. In this case, I would divide both sides by 4, and you'd end up with 1/2 is equal to a. So the final equation of this particular parabola then would be y is equal to 1/2 times x minus p was 0, so we're just going to ignore that, times 1/2 x squared minus 1, like such. And you could include in there, you could rewrite this in a different way if you preferred. You could write it as x minus 0 squared, but that simplifies down into y is equal to 1/2 x squared minus 1. So either one of those two would be fine in terms of your solution. So again, what we're going to do for each one of these is um, we know that for each one of these questions, we are going to be able to pick our vertex and plug that in, and then we're going to be able to solve. We're going to be able to solve for one of the points that we know exists. So this is my favorite point right here. I'm going to choose that one there. And so when I plug this in, I have y is equal to a times x minus. Well, I know what my vertex is. My vertex has an x value of 4, and it has a y value of 2. And then I'm going to plug this point into that equation. So y value of 1 is equal to a times 3 minus 4 plus 2. And this should be squared. So 1 is equal to a times negative 1 squared plus 2. Let's get this 2 over to the other side. So I have negative 1 is equal to a times 1, which in other words just means that a is equal to negative 1. So I can write the final equation of this then, saying that a is equal to negative 1 times x minus 4 squared plus 2. So again, what I'm doing is I'm picking the vertex, picking my favorite point, and then solving for a using that point and using the vertex as well. That's the second example. We'll do the third example here in green. I am going to choose this point right here because I like that one there. So y is equal to a times x minus, this one has a value of negative 5, so it'd be x minus negative 5 squared. And then it doesn't have a y value, so it would be plus 0. Solving for this, we have a times x plus 5 squared. And then what we would need to do is we would need to plug in our point for x and y. And our point here was y value of 3 is equal to a times negative 2 plus 5 squared. So 3 is equal to a times, in this case, this will add to 3, so it'll be 3 squared is 9, so a times 9. We would need to divide both sides by 9. And what we'd end up getting then is we'd end up getting 1/3 is equal to a. So for our final equation then, we can say that y is equal to 1/3 times x plus 5 squared. And that's the final formula for that graph there. Does anyone have any questions about that particular example? Or those three examples, I guess? Again, the steps, I'll write them out on the side here, are write out y is equal to a times x minus p squared plus q. Fill in the vertex point. That's p and q. And then the third step would be choose a point for x and y, for x and y. Plug into the equation. And then the last step there would be to solve for a. So those are the 5 steps that we followed. Okay, if no one has any questions, then we'll jump down to this next step. So what we've been doing is we've been graphing these on Desmos, and then from that graph on Desmos that we get, so for this example, from this telling the teacher or telling whoever that we're calculating this information for how many x-intercepts there would be. There is a way that you can do it without actually ever graphing it. You can predict how many x-intercepts there will be. We said that for every single graph, there will be one, two, or three, one or two, or zero was what I wanted to say. Zero x-intercepts, not three x-intercepts. And that will depend on where the graph actually falls. So I'll set up three scenarios. There's one. Let's just copy this. There's two, and there's three. So these are the three different cases where we could have different x-intercepts. We could have one x-intercept if we have the vertex occurring on the actual x-axis. So we have the vertex occurring on the x-axis. We can have two if we have graphs that look like this, or if we have graphs that look like this. There's 2 points in which they're crossing the x-intercept. Or we could have zero if we have graphs that look like this. And so what we need in terms of the information is, well, we need the direction of opening and we need the vertex. Those are the only two things that we actually need to determine the number of x-intercepts. We need the direction of opening and we need the vertex. So looking at a graph, I'm going to just fill in some dummy graphs down here. Oh, I don't want red, I want black. Fill in some dummy graphs down here. And all I'm going to do is I'm not going to actually graph these. I'm just going to estimate where these graphs are and use that information to try and come up with a fake graph or a graph that works for me. So looking at this first formula here, I have y is equal to 1/4 x plus 2 squared minus 4. So I have 1/4 x plus 2 squared minus 4. My vertex in this case would be -2 comma -4. So -2, -4 is roughly about there. Again, I'm just estimating where this graph actually is. The other thing that I know is I know that this graph, because this a value is positive, I know that it's going to open in the upwards direction. I also know that because it's a value, a is a value smaller than 1, it'll also be a pretty wide graph. So you can kind of predict what this parabola will look like and say that, well, I'm guessing this will have 2 x-intercepts. The luxury for us is we have technology to confirm that. So I have 1/4. I have y is equal to 1/4 bracket x plus 2 bracket squared minus 4. And so as you can see, that looks roughly about the graph that I had drawn on my OneNote. I predicted what direction it was opening. I figured out what the vertex was. And then from that, I could say, yeah, this is going to have 2 x-intercepts. Second example. Looking at some key features here, that right there is a negative a value. So I'm assuming this is going to open down. I also know that my vertex will be 7, comma, -1. Again, the key thing that many of us will get stuck on here is this negative value. That negative value is permanently there. And so what you want to look at when you're looking at P is just this right here. If the negative sign changes to a plus, as in our third example, then that means that the P value was a negative. So we have a vertex here of X value of 7 and a Y value of -1. So I'm going to guess roughly there. I know that this is pointing down and it's also a -5. So I know that this is going to be a super skinny graph. That. So I'm predicting that this one will have 0 x-intercepts. Let's check. We have the equation of y is equal to -5 bracket x minus 7 bracket squared minus 1. And you can see that we have a super skinny graph below the x-axis, and we have 0 x-intercepts in this case. So again, we were successful. Last example here we'll do in green. Again, we have a negative a value, so this opens down. And because this is a positive 4, I know that this will have an x value for the vertex of negative 4. And there's nothing here. And so because there's nothing here, I know that this value for y will be 0. So I have a value of negative 4 comma 0. Now in this case, as soon as I see that y value of 0, I actually don't even need to decide if this is opening up or down. It doesn't matter. I know that if this y value is 0, if this vertex q value is 0, then we have one x-intercept. And I also know that this opens down, so I can simulate what that graph will look like. Checking it in our Desmos, we have y is equal to negative 2 bracket x plus 4 bracket squared. And you can see that there is our graph. I think I actually drew this on the wrong side, didn't I? No, I did on the right side. Awesome. So that's what that graph looks like there. Again, vertex at negative 4 comma 0, and then it opens down, so it only crosses the x-axis at one point there. Bottom question here says, does the value of y, or does the number of y-intercepts never change? And the answer is no, there is always one. And that reason is if we have, again, that's in red, I don't want red. If we have our little graph here, it doesn't matter where I actually put this parabola. So I'll just draw a little parabola there. I'll select it. It doesn't matter where I put this parabola. At every situation, it will always cross the y-axis only once. It doesn't matter where I put this, doesn't matter where the vertex is. It'll only cross the y-axis once ever. All right. So that was the second part of lesson 2. Does anyone have any questions at all?